Hi, in this video we're going to look at integers in Python. So the integer obviously is the int data type. We've seen that before. It's an object, like everything else in Python. And intuitively we know what integers are. It's the numbers, right? It's the integral numbers like 0, 10, the negative ones like -10, maybe big ones, 100 million, 2 billion, 2 trillion, and so on. So the question that comes to mind is, well, how big can they become, either positive or negative? So in other words, we're really thinking about what's the largest magnitude, right? The magnitude being the absolute value. So let's not worry about the sign. How big can that become? So first, in order to understand that, we have to look at how integers are stored in a computer. Well, computers only use binary. They use bits, zeros and ones. And everything is represented using zeros and ones, including numbers. So our integers are represented using binary, base 2, not decimal. So let's take a look at a number. Okay, when we're working in base 2, these are the numerical values of each digit that we have in our number. And here's our number, 10011. That's a base 2 number. And these are the individual bits of that number, right? The bits being 0 or 1. So to find out what the decimal representation is of this binary number, we just add up 1 times 16, 0 times 8, 0 times 4, 1 times 2, and 1 times 1. Okay, that's what we have. And when we add all that up, we get 19. In other words, 10011 base 2 is equal to 19 base 10. So representing that decimal number 19 required 5 bits. Right? We needed 5 bits in order to store and represent 19 in binary, in base 2. So we might ask the other question. What is the largest integer number that can be represented using 8 bits? Right? How far can we go? Well, let's assume first that we only care about non-negative integers. That's 0 and up. We don't care about the negative integers. We'll bring that back in a bit. Well, that means that we have 8 bits to work with. Right? So these are our 8 bits, 1, 1, 1, all right, 8 times. So then a number that we can work with is 128 plus 64 plus 32 plus 16, etc. Right? And that's equal to 255. So the largest number we can use is 255, which is 2 to the power of 8 minus 1. Notice the relationship between 8 bits over here and 8 over here in this expression. Okay. Now, if we care about handling negative integers, let's bring that back into the mix. Well, we're going to need to use one of those bits. If we want to stick to 8 bits, we'll need to use one of those bits to store the sign. Is it positive or is it negative? So we'll only have 7 bits that we can work with. So using 7 bits, well, 2 to the 7 minus 1, following the same pattern here, means the maximum magnitude is going to be 127. So theoretically, we are able to represent all the numbers in the range minus 127 to 127. Here, we were, if we only cared about positive numbers, we were able to represent numbers in the range 0 to 255. Now, 0 itself doesn't have a sign. It's neither really positive nor negative, right? It's not considered negative, and it's not considered positive either. So we can actually squeeze out an extra number in this range because, well, we don't need 2, slots in this range to represent 0. And usually the way the numbers are encoded is that it gets added at the bottom. So now we can reach from minus 128 to 127. So here's the formula. If we're looking at using 8 bits of storage for a signed integer, our range will be from minus 2 to the 8 minus 1 up to 2 to the 8 minus 1 minus 1. Okay, that's the general formula. You can put, n minus 1, where n is the number of bits that you want to use for storage. So what about 16 bits? Well, if we want to use 16 bits, 2 to the power of 15 is this number here, 32,768. And our range, therefore, will be from minus 32,768 up to 32,767. That's when we use 16 bits. What about 32 bits? Well, we do the same calculation and we end up with this range, minus 2 billion something to 2 billion something. Now, if we had an unsigned integer type, our 32-bit range would be a lot larger, right? It would basically double up because we're not dealing with the negative numbers. We'd start at 0, and so therefore we expand to the right here, as we'd seen in the beginning of the video. So as a quick side note, which is kind of interesting, let's say you're working in a 32-bit operating system, and if you have done that in the past, you know that there is a limitation to the amount of memory that the 32-bit operating system can use, right? You may have a PC, and you went ahead and bought maybe 32 gigs of RAM, and you put that in, and you fire up Windows 32-bit, and it tells you that you have way less, something under 4 gigs. And you're like, well, what's going on? I've got 64 gigs of memory in my computer. Why am I only able to access 4 gigabytes? Well, memory space, right, is limited by the address number. If you think back to what we've done in the past, well, every variable is just, a pointer to something in memory. That pointer is an integer number that represents the memory address, right, of where that variable's data is stored. Well, those addresses are integers. And so they need to, have a certain number of bits that they can use to store that address. And so in a 32-bit architecture, our addresses are limited to 32 bits, right? So the address itself is limited to a 32-bit integer. So let's take a look at what that means. Well, every address is a byte. So we're looking at the maximum number of addresses, right, which is this number here, but as bytes. That's how many bytes we can, use up, essentially, because that's the total number of addresses that we can use. And each address is 1 byte. So when we do the multiplication, we can convert, this is the number of bytes, and now we can divide by this to get kilobytes. So we're looking at 4 million something kilobytes. Convert that to megabytes, we get 4,096 megs. Convert that to gigs, we get 4 gigs. That's the theoretical limit, right? So that's why if you can throw in more memory into your motherboard, but if you're using a 32-bit architecture, you're not going to be able to address all of that memory. Now, there are ways operating systems can get around that and do other things, but that's besides the point. All right, so that was just a quick side note. So, but basically, the thing is, how large an integer can be depends on how many bits you want to use to store up the integer. So some languages, like Java and C, actually have different data types for different lengths of integers. And so they have a fixed number of bits, and you have to decide as you're writing your code, thinking, well, I'm going to use an integer here. Well, how big is it going to be? What is it, throughout the lifetime of this program, how big is the integer going to become? And you have to upfront kind of design and define, well, I'm going to make it a, pretty short integer because I know my values are going to be, from minus 10 to 10, right? It's never going to go beyond that for some, reason. Other times you may need something that's larger. So these languages, and I'll use Java as an example because it's consistent across platforms, provide you these different data types. So for example, they have the byte data type, and the byte data type, as you may have imagined, uses 8 bits, and it's a signed 8-bit number, which means its range is from minus 128 to 127. Similarly, they have a short, which is a 16-bit number, signed, so minus 32,000 something to 32,767. You have an int, right? Now an int is a 32-bit number. It's a signed 32-bit number, so its range is bigger. I'm going to start using exponential notation here. You also have a long, which is a 64-bit number, okay, which is going to be in that range. And so on, right? There are other things too. There are more, and some languages will also provide you signed and unsigned variants. So you may decide that this is only going to be a positive integer, so I can use an unsigned variable type. So you may have an unsigned int. Some languages allow you to do that. Now Python doesn't work that way. In Python, the int object, because remember it's an object, uses a variable number of bits. And as your number gets bigger, it will just increase the number of bits that it needs to use to store that integer. So it may use 32 bits, 64 bits, 96 bits, and so on. And that's completely seamless to us. So it's kind of important and interesting to know what's going on behind the scenes, right? It's doing that division of the number up into multiple, bits, and it keeps increasing the number of bits as it needs to, but we don't have to actually think about it as we're writing our code. Right? Now, since integers are actually objects, there's also an overhead associated with each of those. We'll see that in the code section. But theoretically, how big can an integer become in Python? Well, it's limited by the amount of memory that you have available for the program. Now, one thing to watch out for, of course, larger numbers will use more memory, right? If you've got a huge integer number, it may require, 128 bits or maybe 256 bits of memory to store that number. But that's not the only thing that happens. As you get larger and larger numbers, especially once you get past the 32-bit if you're working in a 32-bit OS, or 64-bit if you're working in a 64-bit architecture, as you get beyond that point, to do operations, the standard arithmetic operations like addition, subtraction, multiplication, and so on, it will get slower and slower. Right? The CPU is going to have to do more and more work to, let's say, add two integers. Right? In a 32-bit operating system, it might be able to add two 32-bit integers in one operation on the CPU. But if you grow beyond that, well, it's going to take now more than one operation to add, two integers that are larger than 32 bits, because we're going to have to do them in chunks. So again, this is seamless to us, but do be aware that as your integer numbers in Python get bigger and bigger, your computational speeds are going to decrease. Looking at some code, let's just see again the type of integers. So we can say print type of some integer, let's say 100. And as you can see, it's a class of type int. So integers are objects. So we can take a look at how much storage space, how much memory is being used when we create integers. So we're going to first import the sys module, and we're going to use the getSizeOf method that's in the sys module that allows us to find out how much memory is being used to store a particular variable or a particular value. So we're going to say sys getSizeOf, and let's start with the integer 0. And as you can see, it takes up 24 bytes. And we can think of that as the overhead that we get when we create an integer object, because the object itself requires some memory to get created and stored. So we can think of 24 bytes as the overhead. Every time you create an integer object, you're going to use up at least 24 bytes. And then you're also on top of that going to need bytes to store the number itself. Now 0 doesn't require anything more than, nothing, or 1 bit. So we can think of it that way. So we can look at sys.getSizeOf1, right, which is the smallest non-zero integer we can think of. That requires 28 bytes. So as you can see, it used 4 bytes to store that number. 4 bytes being 32 bits, right? 8 bits per byte. So 32 bits used to store 1. Now we can look at getSizeOf, look at some big number. Let's say 1000, okay? And as you can see, now we're using 160 bytes, right? Which is much bigger. How many bits did we use for the actual number? Well, we can look at, if you want to do that calculation, 160 minus the overhead of 24, that's the number of bytes, okay? And times 8 to get the number of bits. So we used 1088 bits. So that's how many bits we used to store this large integer value here, which if you want to see it printed out, there. I'm not going to try and read it out, but that's the integer number. So you can see, you can work with large integer numbers in Python. It's completely seamless, right? We write 1, we write this. We don't have to worry about, trying to fit it inside a, fixed width data type. Fixed width meaning, a fixed number of bytes that it can use to store the value. Okay. Now, I did mention that, over and above requiring more memory to store large integers, it also slows down the calculations. So let's take a look at an example of that. So we're going to import the time library. Again, we're going to do this quasi benchmark. They're not benchmarks, they're just, kind of quick and dirty timings. And the first thing we're going to do is we're going to create a method. Let's call it calc. We're going to pass it some value a, an integer. In this case, we'll pass in. And we're going to repeat an operation. Let's do it 10 million times. 10, 1, 2, 3, 4, 5, 6. Okay? So we'll do it 10 million times. And all we're going to do here is we're going to multiply that integer by 2. So we're just going to double it up. And we're not going to, store it in a variable. We're not going to print it out. We just want to do the calculation. I just want to try and limit, what we're going to time to just the calculation itself. So that's our method. And now we're going to time it. So let's do time perf counter, right? That's our start time. We're going to do that calculation. We're going to pass in, let's say, a small integer, 10. And then end will be time.perf counter. And we're going to print the end minus start. Okay, so very similar to what we've done in the past. So if we run this, well, it took half a second to run. Okay, and depending on the CPU you're running on and the system you're running on and what else is happening in the background, you'll get different values, obviously. So now let's do the same thing. So I'm going to copy and paste this code. But this time, instead of doing 10, we're going to do that big number we saw before. And actually, I won't get that big that fast. Let's do, 2 to the power of 100. Okay, 2 to the power of 100. If you want to see what that looks like, that's, still a fairly large number. So let's do that and let's time it. And it took 0.9 seconds. Right? So as you can see, it started slowing down. Now we can do this one more time. And in this case, I'm going to do that big number we saw before, that 2 to the power of 1000. Actually, I'll go even bigger. How about that? How about 2 to the power of 10,000? How big is that number? Well, that's pretty hefty, right? That's a large integer. So let's go ahead and do that. So instead of 100, we're going to do 10,000. Okay, that's what we had here. Okay, this big number here is 10,000. All right, so let's run that, and we'll have to have a little bit of patience. There we go, 6.69 seconds. So that, as you can see, the performance difference here was a little bit more noticeable than before. So bottom line, you can use arbitrarily large integer numbers in Python. It will handle it seamlessly for us. But we just have to understand that as the numbers get bigger, not only do they require more memory for storage, but the operations will get slower as well. All right, thanks for watching, and I'll see you in the next video.